فهير in chapter 6 you need to know the moments of inertia for different spheres. Okay, so we'll start. The moment of inertia is expressed as I, and I is usually equal to mr squared. This is for a massless particle, مش massless particle, for يعني a small particle. Or you can say for a hollow sphere. Alright, this is the first one. Now for every shape it's different, okay? Let's see here. I equals half mr squared. Sorry, هذه مش hollow sphere, hollow cylinder. I is equal to half mr squared for a solid cylinder. We also have I is equal to 2 over 3 mr squared for a hollow sphere. We have I is equal to 2 over 5 mr squared for a for a solid sphere. So هيدي hollow, التاني هلا solid sphere. You also have I is equal to 1 over 12 ml squared for a rod, a thin rod. And this is if you're taking the axis about the center. If that same thin rod, you're taking the axis, so again, this was 1 over 3 for a thin rod, but what's different now if you're taking the axis about one of the ends? So I expect everyone here to have this memorized, okay? You must memorize this. So you can't solve these if you don't know, you can't solve any questions if you don't know these. And then we're gonna put like a nice thing on the side. Kinetic energy used to be equal to half mv squared. Now this is for 2D motion, not 2D, this is for translational motion, okay, for translation. But now when we're working with moment of inertia, that means we're working with rotations, and kinetic energy now in rotational motion is equal to half mass. Now becomes moment of inertia, and since we're working with the rotation, we don't say velocity anymore, we say angular velocity. So this is the new formula for kinetic energy, half I omega squared. Okay, let's start solving. Question 1 says the parallel axis theorem. I can't write down the parallel axis theorem, I'll write it down. Okay, I'll put here the parallel axis theorem. Parallel axis theorem. Basically, any I, new moment of inertia around any axis, is equal to the original I that you originally took plus md squared, where d is the distance between the two axes. Okay, anyways, what is the parallel axis theorem? Let's apply it here. The moment of inertia of a thin rod relative to an axis perpendicular to the rod and passing through a point located 1 over 4 of its length from the end of the rod is what? Now this is a grid question. We come in the grid, it was the same thing. They said in the grid question, find the moment of inertia of a thin uniform rod relative to an axis perpendicular to the rod and passing through a point located 1 over 4 of its length. They didn't ask us, they didn't give us any numbers. They said like find an expression for it. Here they want you to use the calculation. Now if you ever see this, now if it comes if it comes for a thin rod, I'll give you the formula to use. Okay, but I need to show you how we got that formula, because you're not supposed to have it memorized. They could get you any shape and tell you to find the new center, to find the new moment of inertia. They could come anything. But I'm going to solve this one for you, and since it was the same in the grids, I expect him to bring the same shape again in the exam, so I'll give you the formula for it. Anyways, let's do it. A thin rod, يعني هيك, this is the thin rod. It isn't a cylinder, it's a rod. Okay, its length كله 0.5 meters. With the mass is how much? 200 grams. So I'll just put here m is 0.2 kilogram. Originally, the point that we take for the thin rod, what do we know? What's the I for a thin rod? I is equal to 1 over 12 ml squared. This is originally the I we know, right? For a thin rod. Now we want it, that's if it's through the center. Now let's say it's passing through 1 over 4 from the end of the rod. Yani over here, the new point here is 1 over 4 L. If this is 1 over 4 L, you know what, I'm gonna fix it a bit because that's not ideal. Let me fix this a bit. This point here is at the center, and this is midway, right? If it's at the center, then it's half-half, right? If we have a point 1 over 4 from the end, yani it's gonna be over here. Hold on. 1 over 4 L. Now, we want to find the new moment of inertia. Whenever you're choosing a new axis, not the normal axis, whenever you're choosing a new axis, that means you're applying the parallel axis theorem. That says I new is equal to the I old, or the I center of mass, plus md squared. What's I of the center of mass? It's a thin rod. We know that the I for a thin rod is 1 over 12 ml squared, plus md squared. What's d? D is the distance between the two new center of between the two center of masses, between the two axes. My old axis was the center. My new axis is over here. What's the distance between these two? Isn't it a quarter of the length? Yes. So I'm gonna put 1 over 4 L and akid all squared. Alright. Now I'm gonna give you the I'm doing this in letters, not substituting. I'm not substituting the numbers yet because I want to give you the formula that you can use if they get you the same thing. But maybe they might get you the same question and change it because it's a good question. They might just change the numbers. Okay, if they change the numbers, then you can use the formula I'm gonna give you now. Anyway, so this is gonna become 1 over 12 ml squared plus 1 over 16 ml squared. Now, how can you add these? You have a calculator. You can simply do it here. You get 7 over 48. So you can use this rule, 7 over 48 ml squared, and you should get the correct answer. Let's see. 7 over 48 times the mass. 0.2 times L squared to 0.5 squared. Let's see what we get. We get this. Now this is obviously in kilograms. This is in kilogram meter squared. They want it in gram meter squared. So what do? You multiply by 100, by 1,000, sorry, and you get 7 point. Oh, how they get 730? Let me look at this one. Guys, I solved this in my copy book in class as well, and I got 7.3. I don't know how he got 730. If you have any suggestion, let me know. But for now, yani, I think the answer is 7.3. Okay. 0.2 times 0.5 squared. Yeah, I did this here. Anyway, moving on to the next question. Now I think they ask us to find the rotational kinetic energy. How can you find rotational kinetic energy? Simply, rotational kinetic energy, K rotational, is equal to half I omega squared. Alright, so it's going to be half times. What's this? It's a disk. What's a disk? A disk looks like this, right? Alright, yeah. I was going over this question, and I saw solid disk. I've got to add disk. Disk is half mr squared. Okay, it's another shape. Alright, so again, rotational kinetic energy simply is going to be Ke rotational is half Iw squared. Now, it's going to be half times our I, since it's a disk, I is half mr squared. We're going to put half mr squared times omega squared. Here we have the linear speed, right? This is v. How can I relate v to omega? Isn't v equal to r omega? Yeah. So if I want to replace omega, I can simply say omega is v divided by r, right? So I'm going to do that. So omega, instead of omega, I'm going to put v over r. And since it's squared, I'm going to have to square this as well. Now, what can you realize? This square will become v squared over r squared, right? Now, can't I cancel r squared with r squared? Yes, I can. So it's going to be half times half is 1 over 4 times mv squared. So it's going to be 1 over 4 times the mass 5 times v squared, which is 2 squared, which is you get 5 joules. Alright, so far I think it's easy. These two are good questions, so they're definitely gonna come, huh? Question 3. The figure below shows two solid spheres attached to thin ends of a rod. The the system rotates such that the center of mass of each sphere at a distance of 18 centimeters from the axis of rotation below. Alright. The rod has a mass of 40 grams, and the spheres have each a radius of 3.5 centimeters and a mass of 900 grams. The moment inertia of a sphere is 2 over 5, and that of a rod such that the axis of rotation through its center is I is equal to 1 over 12 ml squared. Alright, yeah, if anytime you have, a system of shapes and you wanna find center of mass, use the parallel axis theorem that we know. I of the new axis is equal to the old I, or I center of mass, plus d squared. This is simply what you gotta do. Alright, so IP, I center of mass is the rod, and it's over here. Okay, and that's 1 over 12 ml squared plus md squared. We have two spheres, so we're not gonna do it for one only. We're gonna do it for two. So 2 times the mass of each one, d squared. Now, also, since it's not just taking it through a new axis, it's a whole other sphere, like it's another shape. You also have to add in not only md squared, you have to also add in the actual moment of inertia of the sphere. Alright, you have to add in the actual moment of inertia of the sphere. So when you do 1 over 12 ml squared plus 2 into not only md squared, it should be md squared plus the I of the spheres. You get me? Because it also has to be the I of the sphere, it can't just be md squared. Alright, since it's another shape, if it was just a rod and you're moving the point from one point on the rod to another point on the rod, that's fine. You don't have to add the moment of inertia because you're still on the same sphere. But now, since you're adding another shape, you have to account for that. Shape. So over here, simply we're going to do 1 over 12 times the mass times the length squared, which is 0.36 squared. Why is it 0.36? Because 18, that's 36, and then make it meters, 0.36. Plus 2 into md squared, so it's going to be 0.9 times the distance between them squared, not between the spheres, between the sphere and the center of mass, so that's 0.18 squared, plus I of the sphere. Since it's a sphere, they told us it's 2 over 5 mr squared, so plus 2 over 5 mr squared. So we're going to put plus 2 over 5. The mass is 0.9. Well, the radius of the sphere is 3.5 centimeters, so 0.035 squared. You get this, and obviously to two decimal places, it's going to become 0.06. So over here, if you want, you can take into the formula. If like you're making a new moment of inertia, anytime you ask for moment of inertia and there's a system, it's great to do I center of mass plus md squared, and if there's an extra shape, you add I of new shape or added shape. And like I told you, since we have two of these spheres, that's why I multiplied all of this by 2. Okay? Anyways, moving on. Question 4. The figure below shows 3 balls connected by a rod that's perpendicular to another one. The rods are of negligible masses, and the rod ball system rotates about the x-axis at an angular speed of 1 rad per second. So they gave you the omega, and they gave you, this is the system here. This is at 4 meters, this is at -2, this is at -5. What is the total rotational kinetic energy of the balls? We want the rotational kinetic energy. What's the formula for rotational kinetic energy? K rotational is half I omega squared. Now, what's I? I, when you have different shapes connected together, you simply have to use the parallel axis theorem, like I told you. I P is equal to I center of mass plus m d squared. Now, the other one here was us attaching to it other shapes, so it's all one system, right? Over here, It's simply 3 balls connected to each other using a rod. This rod here have negligible masses, so I center of mass is 0. How would you find the new parallel axis? That means we're just going to do md squared. Now since we have many, we're going to do md squared for each of them. We're going to do m1 d squared plus m2 d squared plus m3 d squared. So the new moment of inertia will be then first mass 3 times 4 squared, because the distance is 4, plus the second mass 1 times the distance squared, 2 squared. Why am I taking 2 squared positive? And also a distance squared, so okay, it's going to become a positive answer. Plus m3 times d squared, 5 squared, and you get 102. If I plug this in here, you're going to get half times 102 times 1, because omega is 1, and you get 51 joules. Basically, okay, if you wanna ever like find moment of inertia, the net moment of inertia, حتى here, what we did is we're adding up all individual moment of inertias for each shape. So I1, I2, I3. Same thing here. Instead of doing like a million formulas, let's do it like break it up. Over here, Kevin, we found the I for each sphere, and then the I for the rod. We pretty much added it up. Okay, but I did it all in one formula, فit's خربيش جيج. Okay, that's why for question 5, you know, if you do it all as one formula, you're gonna sort of get lost. Let's just split them up into separate formulas and then add them up one by one. Okay, let's find I of each rod one by one. So Ix, the center or the axis is at the end of Ix, so it's simply just gonna be 1 over 3 ml squared, because it's passing through one of its ends. Okay, this is easy. Now Iy, okay, Iy, it centers over here. Now since we're taking the center here, Iy will be the normal moment of inertia of Iy plus md squared, right? So for Iy, it's going to be the normal I plus m times the distance squared. I'll just put md squared. And this is what's the center of mass of y? It's at the center. What they gave us, that's 1 over 2 ml squared. So it's going to be half ml squared plus md squared. What's the distance? What's the distance between the center of mass and the new axis? It's half L, right? This is half the length. So it's L over 2 m times L over 2 squared. Now doing this on your calculator, you're going to get 3 over 4. No, I did shoot 1 over 12. Do it on your calculator, you get 1 over 3 ml squared. Let's do Ix now. Sorry, Iz. Again, same thing, Iz. The center of Iz is over here. It's gonna be same thing. Center of mass of Iz plus md squared, because the axis is not at the center of mass anymore for z. It's all the way over here. Okay, so it's gonna be, since the center of mass, the formula is this for the center of mass, be 1 over 12 ml squared plus md squared, so m times L over 2 squared, because again the center of z is right here, okay, and the distance between that center and this axis is L over 2. Anyway, so you get again 1 over 3 ml squared. How do you find the total moment of inertia? You just add up each one, and you're gonna get 1 ml squared. Someone might ask, you know, why is it 1 over 3 ml squared directly for Ix? Because it's already being taken. Where's the axis being taken? It's at this end over here. And which rod is at this end already? It's rod X. So, and they gave us that the moment of inertia of a rod, if it passes through the end, is 1 over 3 ml squared. So the moment of inertia for X is already 1 over 3 ml squared, because it's at that end already. It's there. It's already there. Okay, so no need to do it. Alright, Q6 now. The figure below shows a wall clock with an hour hand measuring 10 centimeters in length and 55 grams in mass, and the minute hand measuring 15 centimeters in length and 90 grams in mass. Consider the hands of the clock as long rods that each hand revolves at a constant angular velocity. The moment inertia of a rod where the axis passes through one of its ends is 1 over 3 ml squared. Over here, what's the moment inertia of the minute hand? As you can see here, the axis of rotation is through the end of the rod. Is that the middle of the rod? No, it's at the end of it. Okay, so they gave us the expression for the moment of inertia. Okay, and they told us, you know, what's the moment inertia of the minute hand. As you can see here, they want us, the final step here, they want us to calculate the rotational kinetic energy. Well, to do that, you need to do I alpha half I alpha squared. But see, they made us find the moment inertia of the minute, and then the moment inertia of the hour, and then saying rotational kinetic energy. Why? Because the I that you use whenever you have a system is I1 plus I2. It's always you adding up the I's. So if you ever have more than one shape, that's the key. To find the net moment of inertia, find each moment of inertia individually and then add them up. Anyways, let's do this. The moment of inertia of the minute hand is going to be 1 over 3 times the mass of the minute hand. I think they told me 0.90 grams, so 0.09, times the length of the minute hand. How long is the minute hand? 15 centimeters. So it's going to be 0.15 squared, right? Let's do that. Point 15 squared, and you should get 6.75 times 10 to the power negative 4. Then do the same thing here for the hour hand. Hour hand's 10 centimeters, 55 grams, so we're going to change this to 10 on 55 grams, and you get 1.83 times 10 to the power negative 4, which is what we got here. Okay, okay, yeah, which is 1.83 times 10 to the power negative 4. And then find the rotational kinetic energy. KE rotational, I told you KE rotational is half I alpha, half I omega squared. So it's going to be half times the net moment of inertia is both of them summed up together. Okay, so add these two together, 6.75 and the 1.83. Okay, times 10 to the power negative 4, but no heck, I'm adding them first. You get 8.58 times 10 to the power negative 4 times omega squared. What's omega squared? Let's take a look. We don't know how much omega squared is. Okay. Alright, I'm gonna stop here. I'm not gonna continue. I'm gonna remove this here. Okay. Rotational kinetic energy is half I omega squared. These two rods are their own different rods. They rotate at different speeds, right? The minute hand and hour hand rotate at completely different speeds. But for that reason, I'm going to split it into half I1 omega 1 squared plus half I2 omega 2 squared. Alright, this is better, because these two are two separate hands. Now, for the first hand, for the minute hand, what's omega for a minute hand? Omega is equal to theta divided by time, right? Also, omega is 2 pi over period, 2 pi over t, right? So you can do this. I think it's easier. Omega is 2 pi over t, so it's going to be 2 pi over, what's the period of a minute hand? The minute hand takes 60 minutes to do one complete revolution, right? So 60, and we don't work in minutes, we work in seconds. But 2 pi over 60 times 60, which is 2 pi over, sorry, no, the minute hand takes 60 seconds. Wait. The minute, hold up. La, I'm correct. The minute hand takes 60 minutes to do a complete revolution. Yeah, if I had 60 times 60, so here it's 3,600. So this is the first omega, this is omega 1. We're going to call the first one the minute hand, okay? So it's going to be half. The first I is 6.75 times 10 to the power negative 4. Plus the second kinetic, we're going to do half times the second I, which is 1.83 times 10 to the power negative 4 times the second omega squared. The second omega is now for the hour hand. In the hour hand, it takes 12 hours to do one complete revolution. So it's 2 pi over, how much is the period for one complete revolution for the hour hand? It's 12 hours. So it's 12 times 3,600 seconds, yeah? So we're going to put here times 12 over 3,600. Okay, this has to be squared because it's omega squared. This has to be squared because it's omega squared. Sorry, this isn't 12. This is 2 pi. I don't know how I got 12. Whoa, this is what I write here. Times. It's 2 pi over 12 times 3,600. So times 2 pi over 12 times 3,600. Heck. Squared, of course, huh? Squared. Now do this on the calculator. And these questions are very annoying, I'm not gonna lie to you. But they're very unrealistic. I don't know if any of this will come حتى. I doubt, wallah, I completely doubt. بس يلا. Over 2600 on we square plus 1 over 2 times 1.83 times 10 to the power of negative 4 times 2 pi over 12 times 3600 squared. And you get, they want nanojoules, so times, so answer times 10 to the power of 9. What? Okay, you can't. Answer times 10 to the power of 9. And you get 1 to 1 decimal place. Guys, honestly, I'm gonna skip this. But part A, you should know how to do it. How to find the moment of inertia around this point here. So if they give you this point here, because it's a good question. This is the same as question 1. Okay, how to do it? It's 7 over, if they ask you what's the moment of inertia of a point 1 over 4 from the center, from part A, you simply do 7 over 48 ml squared. Mish part A, from question 1, you do this, okay? The proof, I did it in question 1. Go back to question 1 and watch it again, okay? Question 8, over here. Each figure shows 2 perpendicular identical rods. The rods are all of equal masses and length. The dotted lines represent the axis of rotation which the system rotates. Rank in ascending order from smallest to largest the moment of inertia of the axis of rotation. Alright, so over here, if you want to rank the smallest one is going to be this one here, because this is the original. Okay, this is the original one, so it's going to be the smallest one. How do you know it's the original one? Maybe it's a rod, or for a rod, the axis goes through the center. Okay, هيك. The whole point of this is they want to see, is that you know how to use the parallel axis theorem, which is I center of mass plus md squared. Okay, over here, since it's at the center, it's going to be 0. Md squared is going to be 0. Okay, for this one. So this is the least. That's why C is the least. Then we're going to look at the others. Okay, over here, it's 2 rods, by the way, stuck together. 2 rods stuck together. As you can see here, both the centers are on the axis. So md squared is definitely going to be 0. Over here, they want it up here. Now, until you have 2 rods stuck together, this rod and this rod. This, like I told you, whenever you have 2 together, you add each one and add them together. Over here, this center of mass is going directly up, okay, as well as you have the distance that goes like this. So the total distance that you're adding is a 1.5, I don't know if you want to call this L, okay, 1.5 L, okay. Over here, this and this, remember these are the 2 centers we're looking at. The axis now is at the bottom, it's flat, so it's going down. And over here, it's already there. So the total distance that you're adding is only 0.5 L. Over here, it's over here, right? From this center to this center, it's half. And from this center to this center, it's half. So in total here, you're adding 1 L. Okay, over here, we're adding 0 because all the points are on the axis. Okay, so the one that's the highest is obviously going to be A. Then the lowest is C. Then after that is B. Then it's D. So that's why it's C, B, D, A. So pretty much when you see 2 rods and they're asking you the moment of inertia, basically when you have more than one shape and they're forming a system, like I told you guys, the new I is equal to I1 plus I2. Okay, and each I depends on the distance to the axis, right? Isn't it md squared, right? It depends on the distance to the axis. Okay, so over here, if the axis is up here, you want to look at both the center of masses. Menta, you compare it with the original center of mass. This center of mass, it's bigger. The distance to the axis is big. So the distance here is 0.5 L. Now there's another rod, so you have to look at the other rod center of mass. And the distance from the other rod center to the top of the axis is 1 L. So the total distance that this moment of inertia is getting is 1.5 L. Let's take a look at B. B, the axis is at the bottom. Like I told you, you need to compare it with the center of masses. Since there's 2 rods, you have 2 center of masses that you're looking at. This one here and this one here. The one at the top, to go down, this is 0.5 L. And the one down, there's no distance to travel, because it's already on the axis. So the total distance you're traveling here is 0.5 L. Over here in C, we look at, remember, both the center of masses. The center of mass here is already on the axis, so there's no distance it has to travel. The center of mass at the bottom is also already on the axis, because the axis is vertical, so it doesn't need to travel anything. So here it's 0 L. Then over here, the center of mass here needs to go to the axis on the right, and that's 0.5 L. Also, the center of mass on the second rod needs to go here, so it's also 0.5 L. So total 1 L. Which one has the lowest? C. Which one has the highest after that? Then B, then D, then A. This one's very important, huge important question. You must know how to do it, okay? 4 small spheres, each of mass 0.3, are arranged with a square of side 0.5, and they're connected by extremely light rods. What is the moment of inertia of the system about an axis through one of the spheres perpendicular to its plane? So basically, you want to take one of these spheres as an axis. So let's take a sphere 4 as the axis over here. Okay, let's take this as the axis. Okay, so akid, the moment of inertia of 4 will be cancelled out since we're taking that one as an axis. So how do you find I net? It's equal to I1 plus I2 plus I3 plus I4, right? Very easy. Now, these are small spheres, so most people will use 2 over 5 mr squared. This is the mistake where most people mess up. This is wrong because they're saying very small spheres, which so small that the rods they're saying are extremely light. For when you have a very small sphere, like I told you, for a small particle, you simply just use mr squared. Okay? Now, I1 is 0 because we're taking that one, sorry, I4, other way around, which I1. We took I4 as the axis, so we're going to make I4 0. So what does that mean? We just do I1 plus I2 plus I3. What's I1? Like I told you, it's mr squared. So what's it going to be? Mr squared, so it's going to be the mass, 0.3. 1 is up here, the distance between it is 0.5, so times 0.5 squared, right? Then I2 is up here. The mass of it is 0.3 times the distance is not 0.5. The distance between 4 and 2 is not 0.5. This is the diagonal. So you need to use Pythagoras theorem. If this is 0.5, well, this is 0.5, you need to use Pythagoras theorem. You're going to get that this distance is 0.5 radical 2. Okay, so times 0.5 radical 2 squared. Then I3 is going to be 0.3. I3 is over here. Well, there's no diagonal involved, so you just take the distance. So 0.3 times 0.5 squared. Now evaluating all this and adding it up, you're gonna get 0.3. Very easy. Okay, this is the steps you follow. Well, thank you so much for watching, and good luck in your exam.